everyone, I'm Ryan Jackson. I'm going to talk today about the formation of dark matter deficient dwarf galaxies, and this is work that's been done by myself in collaboration with Sugata Kavaraj, Gareth Martin, and the New Horizon collaboration. And if you're interested, here is the link to the paper, which is now published in MNRAS. Just to quickly give a brief overview of my talk, firstly, I'll discuss what dark matter deficient galaxies are and why they're interesting to study. Secondly, I'll give a brief summary of the New Horizon simulation, and then talk about dark matter deficient galaxies in New Horizon and what we find. I'll then explain the formation mechanisms and then give my conclusions. So what are dark matter deficient galaxies and why are they interesting to study? Well, in lambda CDM, we expect that dwarf galaxies are dark matter rich. This is because they have shallow potential wells, which make it easier for processes like supernova feedback to drive gas out of their central regions and quench them at early times. We also expect them to extend the stellar-to-halo mass relation, with M halo over M star values expected to increase towards lower stellar masses. However, recently there's been observations which seemingly challenge this idea, and a growing number of studies have found that there are dwarf galaxies which have unexpectedly low dark matter fractions. Probably the most famous of these was the Van Dokkum paper, which talked about NGC 1052 DF2, which claimed to have found this galaxy had a dark matter fraction of 1. This would mean that its dark matter fraction was 400 times lower than expected. So the existence of galaxies such as this could pose a potential challenge to lambda CDM unless we can find a way that these galaxies can form naturally in such a model. In order to look at dark matter deficient dwarf galaxies, we use the hydrodynamical cosmological simulation New Horizon. And for those that aren't familiar, this is the successor to Horizon AGN, and it's a high resolution sphere of a 10 megaparsec radius, and that's what's being shown here on the right, that the New Horizon high resolution volume is shown by the circle, and surrounding it is the low resolution region, which is the same as Horizon AGN. And it's a zoom in taken from an average density environment in Horizon AGN. So we now have a dark matter resolution of 10 to the 6 solar masses compared to 10 to the 8 in Horizon AGN, a stellar mass resolution of 10 to the 4 compared to 10 to the 6 in Horizon AGN, and most importantly for us to study dwarf galaxies, a maximum spatial resolution of around 34 parsecs, down from a kiloparsec in Horizon AGN. So before we went into detail looking at specifically dark matter deficient galaxies in New Horizon, we first just wanted to have a look at what galaxies looked like when we plotted the stellar mass versus the stellar to halo mass ratio. And this is what we're showing on the right. So we have stellar mass on the y-axis and the halo to stellar mass ratio on the x-axis. And this is taken at a redshift of 0.25. That's just the currently last available time step of the simulation. So any galaxy that is a central, that means it's not in inside the halo of a larger galaxy, is shown by the open circles. And anything that's a satellite galaxy is a closed shape or circle. So you can see that just from this that a lot of the satellite galaxies seem to deviate away from the kind of main locus that's made by the central galaxies. So what we did when we thought, well, there's clearly something going on here, there's clearly galaxies that appear to be deficient in dark matter compared to centrals. So we looked at galaxies that had a stellar mass larger than 10 to the 8 solar masses. This was just to make sure that they were well resolved in the simulation, even to early epochs, so that we could track their evolution through time. We defined galaxies that were dark matter deficient by ones that had a halo to stellar mass ratio of less than 10, and they're the ones that are given by the blue hex. We then defined a control sample, which is the orange squares, and they were just any galaxies that were satellites, but were within our mass range that we were looking at, and had comparable halo to stellar mass ratios to those of central galaxies in a similar mass range. And then we had a dark matter poor population, which was just the satellites that fell in between our dark matter deficient and our control sample. So the first thing we wanted to look at was how do the median properties of these galaxy populations vary across time. And so on the right, we show how the top panel is showing how the stellar mass of these populations evolves with time. The middle panel is showing how the halo mass evolves with time. And the bottom panel is showing how the halo to stellar mass ratio evolves with time. And the color coding is just the same as it was in the previous slide, as you can see in the legend. So the stellar mass, as you can see, of all the populations seems fairly consistent with one another. Therefore, variations in the star formation that happens inside these galaxies is unlikely to be the cause why they appear to be dark matter deficient. However, when we look at the halo mass, you can see that for the dark matter poor and the dark matter deficient galaxies, there's a sharp decline in the halo masses at late epochs. The control and the central galaxies don't show this decrease in halo mass. They continue to grow as you would expect. And the halo to stellar mass ratio has a similar trend, and it's clear, therefore, that this is driven by the decrease of a halo mass rather than an abnormal increase in stellar mass. So after looking at the median properties and how they evolve with time, we thought it would be a good idea to look at the location of these galaxies and an idea of the environment that they find themselves in. So the top three panels are just showing three different projections of all the galaxies in the simulation. And you can see that these different populations are spread throughout the simulation. They're not all congregated in one area, although they do generally seem to be bunched into areas where there's a congregation of lots of galaxies. They don't tend to exist in the voids, for example. One key thing is that they seem to, or at least mostly, avoid the outskirts of the simulation. This is quite important because as this is a zoom in, but we still resolve the larger horizon AGN region, but at low resolution, it's possible for low resolution particles to enter the high resolution region. And obviously this could play havoc with dwarf galaxies and could cause very spurious results. So we wanted to make sure that this wasn't contaminating these galaxies and creating unphysical results. And the bottom panel shows the 3D local number density for the different populations versus the look back time. And you can see that for the dark matter deficient and the dark matter poor galaxies, these tend to exist in higher density regions than the control sample and much denser regions than the central population. So it appears to be that these galaxies are in higher density regions of the universe. So now that we know that the deficiency in dark matter is being caused by a reduction in the halo mass, and that these galaxies exist in denser environments than the control sample and the central galaxies, we can ask the question, well, what's causing the dark matter to be stripped? And to do this, we invoke the Perturbation Index, which is a measure of the strength of the tidal field around a galaxy. And we define it as, for a galaxy in question, it's the mass of the halo of galaxy I divided by the mass of the halo of the galaxy in question, multiplied by the virial radius of the halo of the galaxy in question, divided by the distance to galaxy I cubed. And then we sum that up for I number of galaxies. So on the right, we're showing the total perturbation index from all the galaxies around it, versus the perturbation index from only the most massive companion. And then histograms showing the distribution of these properties. And what we find is that dark matter deficient galaxies and dark matter poor galaxies show larger total PI than the control sample, and also they show a larger pi from their most massive companion. So this implies that it's most likely this massive companion that's impacting the dark matter stripping, rather than lots of smaller galaxies or lots of flyby events that are disrupting the halo. So here we're just showing a case study of a dark matter deficient galaxy on the left and a control galaxy on the right. So looking at the dark matter deficient galaxy, the top panel is the stellar mass, and you can see that that's increasing as normal. The second panel is the halo mass, and we can see that there is a clear decrease in the halo mass. The third panel is showing the halo level. So when it's a level 1 halo, that means it's a central galaxy, it's not inside another galaxy's halo. Whereas when it becomes level 2, it's inside the halo of another galaxy. The fourth panel is showing the perturbation index, and we split this into perturbation from larger galaxies, perturbation from smaller galaxies, and perturbation from similar mass galaxies, and then the total perturbation. And then finally, we show the halo to stellar mass ratio. So you can see that for this dark matter deficient galaxy that there's a very clear, when it becomes a level 2 halo, that coincides with a decrease of its halo mass. It's being stripped. Whereas looking at the control galaxy, when this galaxy becomes a level 2 halo, we don't see the same level of stripping. So there must be something specifically about the dark matter deficient galaxy when it becomes a level 2 that causes its dark matter to be stripped. So an obvious thing to look at is the properties of this massive companion, to see if there's any clear differences between the three populations. So the top panels, we're showing the halo mass of the most massive companion, the stellar mass of the most massive companion, and the ratio between the dark matter deficient galaxy and the central galaxy. And we can see that the distributions and the median values for these properties are fairly similar among the three different populations. There doesn't appear to be a clear difference between them, and therefore we think it's unlikely that the properties of the central galaxy are causing the stripping. However, in the bottom panels, we plot the orbits of these different populations, and we can see that the dark matter deficient and the dark matter poor galaxies orbit closer to their central galaxy than the control population does. So just to show this a bit more explicitly, we looked at the distance between the satellite and the central galaxies. The panel on the left shows the minimum distance during the orbit between the satellite and the central galaxy. The middle panel shows the distance at every point during the orbit. And the panel on the right shows the same thing, but in kiloparsecs rather than in normalized units, so you can get an idea of what scale these distances are. And so we can see that for dark matter deficient galaxies in blue, they not only have the closest minimum distance, but they're also closer to their most massive companion throughout the orbit, compared to the control sample in orange. And dark matter poor galaxies fit nicely in the middle between these two populations, implying that there's some sort of intermediate population. To get an idea of where the dark matter is being stripped from, we looked at the density profile of the halos. So that's what's being showed on the right here. We're showing this density profile at 3 different epochs during the simulation. The maximum mass corresponds to the point where the halo is at its maximum just before the stripping starts to take place when the galaxy becomes a satellite. Then we have the middle of the stripping, and finally at the end of the simulation. And we can see from these profiles that the dark matter stripping takes place at the outskirts of the halo, where the dark matter particles are more loosely bound. So in conclusion, we've used New Horizon to explain the formation of dark matter deficient galaxies, which have been seen in observations recently and pose the potential challenge to lambda CDM. But we find that these galaxies form naturally in large numbers due to dark matter stripping, and this stripping is caused by interactions with a more massive companion. This dark matter stripping is also responsible for the spread seen in the stellar-to-halo mass relation, and we've offered some identifying features to find dark matter deficient candidates in future observations. Thank you for your time, and I'll take any questions.
Any questions for Ryan?
I have a question.
Jeremy? Sorry, Romain. Jeremy, vas-y.
I'll be quick. So I have a very small question about are you sure that did you check that all galaxies were formed in isolation, or is it possible that you might be contaminated by tidal dwarf galaxies?
So the first part of the question, we didn't find any in isolation. So these were all galaxies that were satellites of another galaxy. What was the second part? Sorry.
Are you sure that you're not contaminated by tidal dwarf galaxies?
Yeah, so we had a look. So when we did the analysis, there were some galaxies that seemed to kind of pop into the simulation into existence. And so when we did the analysis, we made sure that we removed those and only considered ones that had been around for a long time.
Romain? And then
Yes, my question is about the definition of being a dark matter deficient. Am I right if I understood that within the galaxy radius, so within the stellar radius, your dark matter content is perfectly fine. It's only the very outskirts of the halo that have been depleted from the dark matter, right? So if you somehow measure the dark matter content within, let's say, the half-light radius, then it's normal dark matter fraction, right?
That's not something we checked. So we only considered the dark matter content within one virial radius. We didn't check it over different radiuses. So looking at like within the stellar content or something like that. Yeah, we were just trying to get an idea of the total dark matter. I think Junsu has a question.
Yeah, okay. I have small questions. As I know, your horizon has a group size halo around 10 to the 13 solar masses. So are those dark matter deficient galaxies something related to with those massive halos or not?
Sorry, I couldn't really hear. Could you just repeat that? Sorry.
So are those dark matter deficient galaxies are related with massive halos in the New Horizons simulation around 10 to the 13 solar masses?
I think I'll just share the screen. So this was the distribution of the massive companions that these galaxies are around. So some of them are around the very massive ones, but most of them there's a distribution of masses for the central galaxies that they were associated with.
Okay, thank you.
So can I ask a question?
Yeah.
Yeah. So what halo finder did you use to detect the dark halo in your?
Yeah, this is using the adapter hop catalog.
As I know, there is a danger of misdetecting the dark matter mass when the halo passes the dense region, like central region of the host galaxy. Did you take account for that?
Yeah, so we were really concerned about this as well. So what we did when we were kind of sanity checking that there wasn't something funny going on with the halo finder. I mean, firstly, we thought, given that if you look at the example here, so this is kind of 2 gigayears almost of continuous decrease. So that would be a continuous error over and over and over again of the halo finder. But also we plotted the individual dark matter particles and tracked what they were doing in the simulation And so you saw that they formed these quite nice tidal tails as they were pulled out of place and then stripped off the halo. But yeah, that's something that we were very cautious of because it is a problem.
Okay, thanks.
Can go for the next picture, I think. No, Sukyong, you have a question?
Are you giving me a chance to speak up?
Go ahead.
Go ahead. Okay. I was not planning on asking a question, but Amandine was waiting just too long.
Yeah, sorry. I was hoping that someone else.
All right, now I need to go
have a
to bed.
question.
But before I go to bed, I have just a small comment or question to Ryan.
Go ahead.
Yeah. So dark matter deficient galaxies are empirically found in dense areas more easily, right, than in field environment.
Yeah.
And New Horizon is not really exactly a dense environment, right? So what is your suggestion? So even small groups, such as the ones found in New Horizon environment, are effective on making dark matter deficient galaxies? And what do you expect to see in, for example, cluster simulations?
Yeah, so as you said, there's not really any high density regions in New Horizon. And we found that these things formed sometimes between just a pair of galaxies, sometimes in a larger group in New Horizon, so that they spanned a wide variety. It just depended on the ratio, how close the satellite got to the larger galaxy as it went around in the orbit. So I guess naively, I would expect that in a cluster simulation you would find a lot more. That's something that would be interesting to look at with WISE-X. But this is similar to what they found in observations, or at least things like the Van Dokken paper. That was, just a small group environment. It wasn't a cluster. So this wasn't unexpected that we would find it.
Okay, thank you.
Then let's move on to the next talk. Thanks very much, Ryan, again.
Thank you, everyone.
And the next talk is about Martin Ray.
Yes, should I go ahead? Or, yeah.
Yes.
Yeah, thank you. Yeah, so hello everyone, I'm Martin Ray. It's been a while since I've been at the Ramses user meeting, but I'm still using Ramses. So I've just moved to the University of Oxford, but today I wanted to show to you a project that we've done with the group in London while I was there last year with Oscar Aggerts, Eric Anderson, Florent Renaud, and in particular a master student, Matteo Pragomet, whose result I'm mostly presenting today. And so I'm going to skip quite quickly on the fact that we all want to know and understand how star formation is regulated in galaxy, that we don't fully understand feedback and massive stars. But the case I really want to make in this talk is that there are specific regimes where we can learn a lot on these aspects. And in particular, lower mass galaxies are increasingly sensitive to the details of how we do stellar feedback because they live in such shallow potential well. And the good news about this is that every time we build a new photometric experiment, we learn more about faint and ultra-faint dwarf galaxies. So here I'm showing you the census of what we knew about dwarf galaxies as a function of their stellar mass and optical sizes until 2005. And the reason I'm cutting at 2005 is because 2005 is SDSS, one of the first wide sky deep photometric survey. And as soon as we got this data release, we doubled the number of dwarf galaxies that we knew. And then we built DES and PenSTARS, and we doubled again the number of dwarf galaxies that we know about. And so every time we build a new photometric experiment, we keep finding fainter things. So there is a case that what we knew 20 years ago about faint dwarfs isn't fully set in stone. And actually things like LSST or Euclid on NC Roman Space Telescope will probably discover even more dwarf galaxies. And we really yet to fully interpret these observations and understand what they can tell us about feedback and galaxy formation models. And so here comes the EDGE simulation project. So it's an ongoing effort that's been going on for a few years to try to model and understand the formation and evolution of the smallest, tiniest dwarf galaxies in our universe. So I won't go too much into details. You're welcome to ask me questions about it, but we beat the dynamic range by using cosmological zoom simulations, so that of isolated ultra faint dwarfs, so that we can actually resolve their interstellar medium in an enormous amount of detail. And in particular, I want to stress that this 3 parsec scale here is not just an incremental factor of 2 or factor of 8 in resolution. It's actually reaching physical scales where we can resolve the individual explosions of supernovae within the ISM. So that takes out a lot of the uncertainties that we have about modeling supernovae. And so there is a very detailed stellar feedback model with type 2, type 1a, winds. We will see some of the simulation also include radiative feedback. And so the first thing we did with this project was to pick our favorite ultra faint dark matter halo and run it with all these bells and whistles all the way to redshift 0. And when we did that, well, when Oscar did that, sorry, what we found was this. And then we were very happy. It's right in the middle of the observational cloud. It's like, grab a beer, go home, we saw galaxy formation. The problem was then Oscar started to run some other tests. So this is what happens if you increase the supernova energy by a factor 10. And this is what happens if you limit supernova feedback very strongly in terms of winds, in terms of the velocity and temperature of the winds of the ejecta, sorry. And so we started this entire project thinking, well, dwarf galaxies are super sensitive, but we can actually increase supernova energy by a factor 10 and still get something that is within observational constraints. So suddenly it wasn't looking so pretty. And it's only really when we started doing things like turn off all feedback channels that we got unreasonably compact and bright galaxies. But I guess no one really learns that much from that anyway. And so we were facing quite a big problem because it turns out that it's actually quite hard to discriminate between ISM models using the structural properties, the photometric properties of a small number of ultra faints. And so there's only really 2 ways forward in this. And one is just to accept this fact and to simulate more histories and objects to understand how your physics deal at the population level and whether your population is compatible with the observed population. And that's kind of the route that I took in some earlier works. But today I want to focus more on the idea that there are other observables, and in particular spectroscopic observables that we can quantify that might be more sensitive to these model changes. And in particular, we realized quite quickly that the amount of metal, so the average metallicity in this galaxy, was much more sensitive to our assumptions and the feedback modeling that we did in this very, very faint dwarfs. So if we repeat this exercise, you can see that if we increase supernova feedback here, galaxies do get fainter, but they blow away their metals much more, which meaning that they are now in tension with some of the observed faint end of the mass metallicity relation. And actually this trend goes even more. The no feedback is extremely rich for its stellar mass. And if we keep going this way, we get even totally iron poor galaxies. And so we found our sensitive observable. One of the key takeaway points from this paper in 2020 was that the metal retention and the amount of iron within these galaxies is actually a very sensitive probe of ISM modeling. And it doesn't stop here. It's also, so supernova feedback can be, you just need to get the exact right amount of it and right amount of coupling of it to avoid blowing out your metal too much. And all of that doesn't really stop here, because we also realize when starting to compare with the literature that the faint end of this mass metallicity relation was a very big problem for most modern simulations of ultrafaint. So here I'm showing you the results from Coral Wheeler and the Fire Galaxies population of ultrafaint, some from Elad Appelbaum from Chang'e, and from Andrea Mathieu and the Nihao group. And the basic point is that this faint end here that is observed is a real challenge for current modern simulations. It's actually really hard for us, and I want to say all of us, to produce galaxies that are faint enough in this bottom left corner and yet retain enough metal to match the enrichment of what is observed. And so with all of that in mind, we started a project with Matteo, our master students, to see whether we could use this sensitivity of the mass metallicity relation to test some other more exotic ISM models. And in particular, we started looking at the idea that the IMF might be varying with ISM environments. So I think most of you will be aware that the IMF is observed to be classical and universal in the Milky Way. But there's actually quite a body of evidence that the IMF might be bottom heavy in massive elliptical galaxies. And on the other side of the spectrum, in dwarf galaxies, it's been repeatedly observed to be bottom light. And so I think it's fair to say that we don't really know whether the IMF is systematically varying or not. And if it is, what is driving this variation, whether it's something about metallicity increasing from the left to the right in galaxy properties, something about cooling and fragmentation, or there's something more about dynamics and like the fact that velocity dispersion also increases and so on. But if you take this observational results at face value and just accept that you have a bottom light IMF, which if you assume a given shape, it turns into a top heavy IMF, that means that you make very strong modifications to the feedback budget that is available in your ultrafaint dwarfs. And that might have measurable consequences on their iron content. And so what Matteo did was to implement a metallicity-dependent IMF in our Ramses simulations, according to the empirical relation determined by Marley Giha in 2013. And so the idea is that at solar metallicity on the right, the IMF has a high mass slope that is the kind of classical value, whereas it goes towards more top-heavy IMF as you go to lower metallicity. And so this has very direct consequences, as I said, on the feedback budgets, because a more top-heavy IMF means you have more supernovae in each stellar population as a function of their birth metallicity here. And so in the range of metallicities for ultrafaints, this means that you boost the number of available supernovae by about a factor 2. And that might not be very good because, as I said, too much supernova feedback blows away metal. But actually what we realized quite quickly is that you also change quite significantly the yield of metals because you're overproducing massive stars, which produce much more metals than low mass massive stars. So you're also boosting the iron production within each of this stellar population of your dwarf galaxy. And so that means that once you resimulate this one galaxy with the same cosmological setup, but this IMF, this varying IMF scheme, you actually get something that is up here. And that's because it's fainter because you've increased the supernova budget, you're reducing the stellar mass. But it's actually more metal rich because you're also you're matching this increase in supernova budget by an increase in metal production. And so this was all kind of like a little surprising. And we also realized with Oscar that there was other star formation and feedback that might enter that might be at play in these galaxies, and in particular. Oscar ran a test where we turned on radiative feedback, photoionization, and photoheating with Ramses RT. And then we got an entirely different result because radiative feedback starts operating from basically the birth of each stellar population. There's no runaway star formation waiting for the first supernovae to turn, for the first massive stars to turn supernovae. And that means the regulation mode of star formation is completely different. You have much less outflow and much more metal retention. And so that means that you are actually able, so in this case here, you're metal rich because you're overproducing metal. Whereas here, you're kind of metal rich because you are keeping your metal within your ISM. And so the last thing that Matteo did was to combine these two effects together, hacking Ramses RT to correct for the IMF change, and in particular, boosting the luminosity to reflect the fact that as the IMF becomes more top heavy, there's more available flux in each photon bins, And so when you combine these two effects together and you end up with the most complete model that we've made so far, which is the metallicity-dependent IMF and including radiative feedback, you end up all the way down there. So you end up with something very faint because you have a lot of feedback in it, but actually still very metal rich due to this combination of increased metal retention and increased metal production. And so a more top-heavy IMF leads to very faint yet enriched dwarf, and we were kind of very amused, like surprised, I guess, by this result, because we started this project thinking that we could probably rule out IMF variations.
3 minutes.
That we could probably rule out IMF variations thanks to dwarf observation. And actually, so far, it's proven a framework that not only produces reasonable galaxies, but also helps us in solving this kind of challenge of the faint end of the mass metallicity relation. So I really want to stress that I don't think this should be interpreted as we need IMF variation to solve this problem. There's probably many other ways in which metal enrichment and metal retention goes wrong in our ultra-faint simulations. But nonetheless, I think it's an interesting enough result to warrant more investigation and future consideration of IMF variations. And so that brings me to my conclusions, where I hope I've convinced you that the faint end of the mass metallicity is currently quite a big challenge for galaxy formation models. There's a lot to learn about feedback, looking at ultra faint and in particular how much metals they retain. We've shown that an increasingly top-heavy IMF at low metallicity self-consistently produce this faint yet enriched dwarfs. And it does so by the combination of overproducing metals and radiative feedback, which is key to a calmer regulations of star formation. And I want to stress that over-effective supernova feedback is not good, because it does create faint things, but they blows away their metal so much that they are completely iron poor. And so I'll leave you with these 4 points, and I will take any questions that you might have.
Stan, and then Sugata, Johan.
Thank you. Yeah, thank you for the nice talk. I just have a short question. Do you include type 1a supernovae in your model?
Yes, we include a delay time distribution and individual sampling for type 1a. Individual sampling for type 1a supernovae.
Okay, thanks.
Sugata.
Thanks. Thanks, Martin, for that interesting talk. My question is a quick one as well. What kind of stellar masses are you looking at for your dwarfs? Because you only showed V-band absolute band.
Yes. So this is about 10 to the 4 to 10 to the 5 stellar masses. And here you're looking at 10 to the 3 stellar masses of total stellar mass within like 2 Aflar radius.
Okay, so these are more stellar cluster-like than galaxies, I guess, right?
They are, but they are embedded in the dark matter halos, in the dark matter halo. So then it's very tricky to differentiate globular clusters or cluster in general from dwarf galaxies. But these are modeled to be galaxies forming from a dark matter halo at high redshift.
Okay. So, so Ryan Jackson wrote a paper on not galaxies which are as low mass as what you're looking at, but we also looked at not metallicity, but the spatial distribution of stellar mass and stuff like that. So I think it'll be interesting to connect with your results at some point, because we're also using the same code, I think the same kind of baryonic physics and things like that. But,
interesting. Yeah, just ping me after the talk. I'd be happy to catch up.
Yeah, I think Ryan can probably ping you. So I mean, in Ryan's paper, the lowest mass was like 10 to the 7 or so, maybe 10 to the 6.5. So it's well away from what you're looking at. But there should be some sort of continuum at some point, right, for these for the evolution of these properties. But anyway, thank you.
Interesting. Yeah. So we'll hear. I think just after me, we'll hear from Ethan from another project going to higher masses. So you might be interested in following that as well.
Sounds good. Thanks, Martin.
Johan and then Tyson, if you still have a question, given that your hands suddenly lowered.
So you mentioned that you have a type 1a supernovae. So I don't know to what extent this is the iron content in that case is sensitive to the contribution from type 1a. But the problem of type 1a is that the supernova rates and or their time delay is not very well constrained. I mean, in general, it's only constrained by a large sample, and this might differ for low mass objects where there are only a few stars. And so I'm just wondering, so I have this question, and I'm also wondering whether other chemical elements might be more robust against the things we don't know about stellar evolution, right? Like elements that have the contribution from type 2 and AGB stars only, for instance.
Okay, so there's several things in this. So let me unpack it a little. So I do agree with you that both delay time distribution and yields in general are uncertain, and that's what I mean by there's many things here that might also explain the mismatch with current simulations. That being said, in this ultra faint, all of the stars form basically within 1 gigayear before they are quenched by reionization. So you don't have so much time for late enrichment by type 1a. So it's mostly, they are extremely alpha over Fe rich. And I forgot exactly what the last part.
If you have any other chemical proxies you can use, like carbon or oxygen or whatever you can think of.
So not in the simulations, but we will hear from Eric Anderson, who's been implementing a lot of individual elements, and we are actually resimulating some of these galaxies with a lot more elements right now. So I can't answer this from the simulations we have, but this is definitely something we're looking at.
Okay, cool, thank you.
Jason, did you still have a question? Otherwise, I will move on to the next talk.
So I will ask a question later on Slack.
Okay, great, thanks.
Thank you.
So the next one is by Ethan Taylor about star clusters and galaxies with an edge. Ethan, if you can start sharing your screen, please.
Cool. Can we see it? Yeah.
Yes.
Cool. Okay, so I'm Ethan Taylor. I'm a part of the EDGE collaboration, which is a collaboration between Lund, UCL, and University of Surrey. And I'm gonna, introduce the EDGE project as well as go into my stuff that I've been doing with it towards the end. Well, this is being designed to resolve individual supernovae in a simulated dwarf galaxy with standard lambda cold matter cosmology. And I'm going to be explaining the motivation for this. So what's different about EDGE, some key science highlights to date, and then I'm going to be focusing on my own work modeling star clusters within the very smallest galaxies. So I mean, I'm sure that we all know here, but what are dwarf galaxies? Dwarf galaxies are the smallest star-forming systems within the universe, very sensitive to feedback processes, and this lets us learn about galaxy formation at all the mass scales. Because of their sizes, they populate the lowest dark matter halos that we know of, and from this we can test cosmological models that gives us insight into the nature of dark matter itself. But there's also an overlap between globular clusters and dwarf galaxies, and this leads to uncertainties in classifications between the two. Cool. So what we can see here in Simon 2019 is the absolute V-band magnitude on the y-axis and the half-light radius on the x-axis. And at first glance, it appears that there's two separate areas of this, the globular clusters on the left in diamonds and the dwarf galaxies on the right. And the dwarf galaxies on the right in blue for confirmed dwarfs, and turquoise for suspected dwarfs. But in that area right there, we can see an overlap between things, and things start to get a little uncertain. And that's what the hollow circles are, systems where we aren't sure if they're globular clusters or dwarf galaxies. And it's this categorization that matters, because the number of dwarf galaxies can tell us about the nature of dark matter itself. And that's because the more small dwarfs there are, the colder dark matter is. So it's important to know what the stellar systems are, if not dwarf galaxies, but actually globular clusters. So one of the main goals of the EDGE simulation suite is to understand this relation, and in fact, that's what's the main focus of my own work. So a lot of simulations go for a top-down approach, and that means initially picking a box size to simulate, and then, as we all probably know, and then picking a manageable resolution. But that causes a subgrid physics model which is reliant on the resolution of the simulation to be altered as you improve it, which makes it harder to get your simulations to converge on a single answer. But what we do with EDGE is go for a complementary bottom-up approach, which instead allows us to fix our subgrid model by fixing our resolution. And we can do this by asking what's the finest details that we want to be able to resolve. And like Martin mentioned just before, for EDGE, that's the sites of star formation as well as the impact of individual supernovae. And it's this that's allowed us to come up with the fixed resolution of 3 parsec. 3 parsec and a temperature floor of 100 Kelvin. And along with this, our fiducial runs have a baryonic dark matter mass resolution. There we go. And along with this, our fiducial runs have a baryonic dark matter mass resolution of 161 masses of the sun and 945 masses of the sun, whereas our high resolution runs have 20 and 118 respectively. Now that becomes extremely resource intensive when you increase the mass range, but there's also a very simple solution to this, and that's just to throw more CPUs at the problem. And that's exactly what we plan to do and are currently starting to do with EDGE 2.0. And that's recently been approved, and it is we're just getting to running some simulations with that now. So we all know astrophysics loves acronyms, and EDGE stands for Engineering Dwarf Galaxies, Engineering Dwarfs at Galaxy Formation's Edge. And it's the first part of that I'm going to focus on slightly here. I guess, again, it might have been mentioned in previous years, but I guess just to mention it for now. So we use a technique called genetic, and that allows us to genetically alter the histories of dwarf galaxies within our simulations. So what we can see here, that's covering there. So what we can see here in the top figure is a reference simulation with 3 other genetically modified dwarfs. And what we've done here is made the reference galaxy form earlier and later to see how this would affect the growth of the dwarf galaxy. And this allows us to investigate the histories of the galaxy and see how they would go on to affect the attributes of the reference galaxy. So our initial void is a 50 megaparsec box, and that's set up with this genetic code. And that's run with Ramses in 2014 Planck cosmology. And we start out all the way at z equals 99, and we run it through to present day. And then we go back and check this void for interesting halos to see what to follow up on and resimulate. Whoops. Cool. Yeah, and then we resimulate them with baryonic matter at a much higher resolution, radiative transfer, or like Martin said, all of the bells and whistles and such. And that's what makes up our individual simulations. And then, yeah, and then when we resimulate them, because of our spatial resolution, we can see a lot of things happen, a lot of interesting things happening within them. So moving on to some key results from EDGE, we find that the EDGE dwarfs give an excellent match for observed properties of low mass dwarf galaxies. And we're currently able to predict new classes of dwarf galaxies, such as ultra diffuse ultrafaints, quench gas rich ultrafaints, and rejuvenator type galaxies. And finally, we move on to we find a new method for lowering the inner dark matter density of dwarf galaxies itself. Now, it's the first 2 points I'm not really going to be talking about too much, but I will show a small movie made by some of the people on the EDGE team. I think Martin and Corentin was some of them, on how that works. So whoops. So yeah, so what we can see here is one of our EDGE dwarfs evolving from about z equals 11 through to the present day, with reionization and happening at about z equals 6. And we can see the individual sites of stars being born, before swapping back to the dark matter, where we can see lots of mergers happening to cause a rejuvenation of this dwarf. There we go. And we'll see in a moment more stars being born, and that's because with that dark matter mergers of the halos, we see more dense regions of gas coming together, which again allows us to form more stars in them regions. And that leaves the M200 of this dwarf at about 4 times 10 to the 9 solar masses, and the solar mass to be about 4 times 10 to the 5 solar masses. And that's just one of the predictions from the EDGE data that we currently have. There we go. Cool. So another thing I can talk about is the results from Orkney et al. 2020, and that concerns the density of the central dark matter out to about 40 parsecs. And what we can see here is that between the dark matter only simulation and the fiducial simulation, we can see a slight drop in the central density. And this is due to stellar feedback, which is currently in agreement with the literature. And this is due to the stellar feedback processes causing the dark matter to move out to an orbit that's further from the galactic core. Now, if we take this exact same dwarf galaxy and genetically modify its initial conditions, we can see that using the genetic modification technique I mentioned earlier, we can see here that the dark matter core continues to grow. And this is because of impulsive heating of the dark matter from the minor mergers that causes the dark matter to occupy an orbit that's further out from the galactic center. And that's interesting because, again, it could explain recent observational hints of a lower dark matter density that's predicted at centers of at least some of the ultrafaint dwarfs, like the one seen in Contenta et al. 2018 and Amoresco 2017. Cool. Then I'm going to briefly talk about the work that I've been doing since October when I started. But the main questions here are, so does EDGE form star clusters? And if so, how? If EDGE does form star clusters, are some of them born in their own dark matter halo? And how can the dynamics of and properties of these star clusters constrain the inner dark matter density in ultrafaint dwarfs? And I won't be answering all of them today, but these are currently the main focus of my PhD project in general. So I will eventually get to all 3 of them. And for the rest of this talk, I'm going to be defining star clusters as systems with no dark matter at all, and dwarf galaxies as systems with a significant amount of dark matter. So within one of the dwarf galaxies simulated by Edge, what I've done here is simply plotted all of the stars within the main halo and then focused in on them. And they're colored by what we've defined as a dwarf galaxy and a star cluster in blue and green. And then there's a small weird region in between the two where it has a significant amount of stellar mass. And I've labeled that the ambiguous stars. And that's where there's more stellar matter than dark matter, and that's colored in red. So what we can see here is that the majority of the group is the dwarf galaxy, with an ambiguous region towards the center. But off to the right, right about here, you can see that there's a star cluster, and that's got, from the halo finder that I've been using, which is AHF, it has no dark matter assigned to it at all. And you can tell this by eye as well. So if you look through the simulations, you can see this cluster and you can see it moving. And again, AHF picks up no dark matter at all. So now we know that Edge does in fact naturally form star clusters, and that in itself opens the door for more investigations to do with them. So I've also extended this definition over a range of snapshots from one of our simulations. And what we can see here is the points. A lot of these points are actually dwarfs. So what we see here in the blue X's are the
3 minutes, Ethan.
Okay. Okay, yeah. So what I've done here is pointed out the blue X's are the dwarfs that you could from the previous slide in blue. The pink squares are the ambiguous region, and then these yellow stars are the star clusters. So if we take this and follow this up for further investigation, we can also see that these groups they get a little bit weird. So what I've done here is that these 3 points right here are pure star clusters from the previous slide. But what we can see now is that there's also 3 more points. So there's 3 more points here, here, and here. My animations aren't working, I guess. Where there's upwards of 90% stellar mass. And by definition, they're not star clusters, but they possess a lot of dark matter. They possess some dark matter. 2 of them fall into the region I called the overlap earlier, whereas the higher one falls directly in with the globular clusters. So the diamonds are the Harris data, the Harris catalog of globular clusters, whereas the green circles are dwarf galaxies taken from Simon 2019 review paper. But it's interesting because groups like these are exactly the points to follow up on, and that's what my current plan is going forward. To see how these groups are formed, as well as their conditions and their environment, but mainly how they got that dark matter that's been assigned to them. And then moving on to my conclusions. Finally, my conclusions. So what we found in our edge simulations is that the dark matter density can be lowered in our edge dwarfs, and this is due to the combination of stellar feedback and late minor mergers. And this could be signs of unexpectedly low central dark matter density in some ultra-faint dwarfs found within the literature. Dense star clusters form naturally within our edge simulations, and with this we're able to reproduce a region where star clusters and dwarf galaxies coexist. And it's this area that I'll be working to develop on and expand in the future. And finally, in future work, I'm going to be attempting to find a way to separate these star clusters from dwarfs observationally, and looking to see how star clusters form within our simulations. And finally, if star clusters can give us constraints on the inner dark matter density of ultra-faint dwarf galaxies. Cool.
Thanks a lot, Ethan. Any questions? Jason?
It's a very impressive work. I have a question about your cluster. So I suppose, I'm not quite sure, but have you run the simulation with different star formation efficiency? I'm asking because these star clusters might have formed just because you have adopted pretty high star formation efficiency for free fall time. So if you can't, get the star cluster with a lower star formation efficiency for free fall time, then things could be a bit different. Can you comment on this?
We have not. I don't think we have run them with a different star formation efficiency, but when we have looked at similar, when I've looked at similar simulations that we have run, all within the Edge suite, we've run a multitude of simulations, lots of them. They all possess star clusters at some point. Yeah.
Okay. Can I have one more question?
Sure, given that no one else has raised their hand yet.
Yeah, I might have missed this, but so your documented halo mass is like 10 to the 9 solar mass or so, is that right?
Yeah.
And as far as I remember, the specific number of the GC at that documented mass is pretty low, and you mentioned you have quite a few. Did I understand correctly, or?
So could you repeat the question, please?
So do you form more GC or clusters than we actually observe in the local universe in such a low mass documented halo?
So I need to compare it directly with the amount that we're expecting in a region like that. But at the moment, I'm not too sure on that. Well, I guess at the moment it's just I know we do form star clusters. I'm not really too sure on the comparison.
Thanks.
Anyone else? Otherwise, we'll move to the final talk of the day by Romain Teyssier, who is going to talk about galactic dynamo. And I don't think Romain needs any kind of introduction.
So, can you hear me?
Yes.
So I'm going to share my screen. Okay, can you see my screen? No.
No.
Okay, give me a sec. Okay, do you see my screen now?
Now we see the paper. It's
okay, good.
Still a tiny bit blurry, so maybe change the zoom factor.
Okay, so welcome everyone. So my issue here is that my laptop died yesterday, so now it's getting surgery today. So I'm using an iPad, and all my slides actually are on the laptop. So I'll have to do it like that today. So the purpose of my talk is to discuss a technique to model the evolution of magnetic fields in the universe. And so I will start by introducing the work we did with Michael Reeder a couple of years ago, where we modeled a dwarf galaxy. So you can see here 6 panels. So each column is a different resolution of the same cooling halo dwarf galaxy. And you see that the resolution is halved each time. You move from left to right. And what you're looking at is the side-on view of the disk at the top and the zoom on the side-on view of the disk at the bottom. And so this is a strongly feedback-dominated dwarf galaxy, which could be, an analog of a high redshift dwarf galaxy. And what we did was to model this very turbulent medium using the ideal MHD solver of Ramses. And what we show in this paper, so let me show you this plot here. So you see the magnetic energy in the galaxy as a function of time. And so if you don't have feedback, that's the result on the left, you don't form this turbulent disk, and you don't get a dynamo, you just get a relatively minor amplification of the field by, let's say, 3 orders of magnitude, mostly due to the rotation of the disk. And you see that there is no effect of resolution. If you increase the resolution, the magnetic energy grows the same way, and it's because you resolve the rotation motions the same way. On the other hand, if you include the supernova feedback and you get this very strongly turbulent galaxy, then what we obtain is a qualitatively different result, meaning that we get the magnetic energy now growing exponentially. That's why they look at straight lines in this log-lean plot. And you also see that the growth rate depends significantly on resolution, which tells us that the growth rate is dominated by the small scale eddies or vortices that are driving the magnetic dynamo. So the learning, the take-home message here of this simulation we performed a long time ago is that in order to get a dynamo that is fast, right? I mean, if you look at the fastest dynamo we get here, which corresponds to a resolution of better than 10 parsec, you see that the time you need to increase the magnetic energy by 7 orders of magnitude, which is not that much, is 1 gigayear. And so, and you need a resolution better than 10 parsec. So the reason is that you need to resolve those small eddies at small scales in order to get a fast dynamo. So for large scale, I mean, for cosmological simulation now of Milky Way size objects, this resolution requirement is too steep. And so we had to rely on another method. And so here I'm going to report on what we did with a master student last year, which is a subgrid turbulent dynamo. So this is a paper here which is in preparation. And this subgrid dynamo aims at overcoming this resolution issue we have demonstrated with Michael Reeder by augmenting the induction equation with an additional term that accounts for unresolved turbulence. So let me go to the theory here. There we go. That's the theory. So you can see here the equations we're solving here with Ramses. So you recognize the conservation of mass, momentum, and energy. And that's the equation of interest here, the induction equation that describes the evolution of the field. And you see that if B is initially 0, B will remain 0 all the time. So you need a seed field. And what I want to stress here is that seed fields come from different scenarios. The most popular one being the Biermann battery, but there are plenty of other scenarios, right? The Biermann battery is actually an interesting scenario because it's based on very robust physics that must happen. There might be more exotic scenarios that justify the higher field strength for the initial seed field, but the Biermann battery gives you an initial field of 10 to minus 20 Gauss, right? So that's the typical order of magnitude you get from these robust plasma physics kind of theories. So if you only rely on the Biermann battery, it means you have to increase the magnetic field from 14th order of magnitude between redshift say 10, which is the end of the ionization, or during the epoch of ionization, and today. And so 14 order of magnitude, it means that the resolution requirements, if you remember what I just said on this study with Michael Reeder, the resolution requirements are probably sub-parsec. So the game here in our subgrid dynamo is to actually modify the equation. So here is the theory. So we consider that we have, for the velocity field and for the magnetic field, a decomposition. So it's a classical mean field decomposition, where we write the velocity field as the sum of a mean velocity field and a fluctuation. And we do the same for the magnetic field, where the magnetic field is written as the mean magnetic field and a fluctuation. And so in this context, the mean velocity field and the mean magnetic fields are both coming from the simulation itself, from the resolved scales. So the Ramses variables related to the velocity and to the magnetic field are given the mean field values. On the other hand, the fluctuations with the primes corresponds to the unresolved scales. that actually are spanning the scale of the cell all the way down to the distribution scales, which are almost microscopic scales. So if you decompose your magnetic field with the mean field and the fluctuation, then you can rewrite a mean field induction equation, which is written here, where there is a new term coming in, which is the fluctuation electric field, which is the average of U prime cross B prime. And of course, we don't know this guy because it's given by the unresolved scales. And so here, that's the classical kind of mean field approach. We rely on the closure relation, which can be written in a very general term like that, where the leading order term in this closure relation is given by an alpha tensor, which is also called the alpha dynamo or the subgrid dynamo, which actually is a tensor, a matrix applied to the mean field magnetic field. Right? And so if you can show that if the turbulence is homogeneous and isotropic, which is debatable if you have a disk, then the tensor becomes a diagonal matrix with alpha being a scalar, right? Or actually a pseudo scalar. And then, of course, your model becomes very simple with this subgrid electric field, this turbulent electric field being proportional to the mean magnetic field, and the proportionality coefficient is this alpha. Okay, so you have a lot of theories and simulation efforts since decades trying to estimate this alpha, and one of the most popular model is based on the kinetic helicity on small scales, and alpha is actually taking this form. It's quite a complicated form, which depends on the curl of the velocity field with the dot product with the velocity field. This is called the helicity. And if you average this helicity over the perturbations, you get an explicit form for alpha. You see that alpha can change sign. It's a pseudo scalar, and it depends also on the correlation time of the turbulence, right? So this is a very complicated model. You can derive actually evolution equation for this equation. So here we really try to explore what this subgrid dynamo can make for us by augmenting the small scales that we don't resolve. And so we tried first a simple model where actually alpha is based on the subgrid turbulence that we integrate already as using an additional equation, an additional variable to describe the kinetic energy of turbulence. So we have this unresolved turbulence velocity dispersion, sigma t, and we multiply by this term, which model the quenching of the dynamo, the idea being that if the magnetic energy becomes actually comparable to the turbulent kinetic energy, this subgrid dynamo should stop because it reached saturation. And so everything depends now. So that's the model we adopt. And of course, it's a simple model. Some people say it's a simplistic model. Depends only on one free parameter, which is this quenching parameter, which controls when the subgrid turbulent dynamo is set to 0. And so, of course, it's a free parameter that we probably think, many people think it's resolution dependent. And so we run this simulation. We run a simulation of a Milky Way-like galaxy with this model. And I'm going to briefly show you the results. So first, what is the influence of this? So that's the influence of the quenching parameter. So we run, so it's not an epsilon, actually, it's a Q. Let me change that. And here we plot the ratio of the magnetic energy to the turbulent kinetic energy. And what we did here was to increase the quenching from very small value, 10⁻⁵, to our fiducial value, 10⁻�3, meaning that the subgrid dynamo stops once the magnetic energy reaches 10⁻³ times the turbulent kinetic energy. So you see that the horizontal line here is this value, this Q parameter. And you see that the simulation managed to amplify the field further. Those are the, oops, sorry, there's a storm here. Sorry for the storm. And you see that these 3 orders of magnitude that we get here corresponds to the rotation and the disk and the resolved scales that are amplifying the field additionally compared to what the subgrid dynamo is. So this is now our fiducial parameter. This Q value is fixed to 10 to the minus 3. It's probably very certainly resolution dependent, meaning that when you increase the resolution, you can lower this guy because the simulation itself, the result scales, are going to take care of amplifying the field further. So the better the resolution, the more you can reduce this Q value. And you see that there is not a lot of point below this, right? So basically what the simulation is doing is that it's very quickly amplify the field to the prescribed saturation value. And then the result scales are taking over, okay? So now let me show you a few results. So this is a phase space diagram at redshift 4. So this is redshift 4 here. And this is redshift 0. And you see that there is actually two regimes here, clearly that emerges. One, that's the initial field, 10 to the minus 20 Gauss. So here it's the magnetic pressure, so it's the square of that. And it follows the rho to the 4/3 ideal MHD scaling relation. And that's basically the collapse here, and maybe an additional minor amplification. Then all these stripes that you see here are galaxies, different galaxies. We have the small scale turbulent dynamo, the subgrid turbulent dynamo is amplifying the field very fast. And then it stops at another relation, which corresponds to the equipartition. And so this dashed line here corresponds to a field which is at equipartition deep inside the galaxy at very high density. And then again, you have the rho to the 4/3 relation. At redshift, and so you see that you have a lot of, at redshift 4, you see that you have a lot of pristine regions where the magnetic energy corresponds still to the initial value. But at redshift 0, and actually there is almost no more pristine region. All the fields have been amplified, and this is mostly due to outflows. And so you see here that our subgrid dynamo, I forgot to say that, our subgrid dynamo only works at gas denser than 10 to the minus 2 h/cc. And so all these guys that you see here are due to galactic winds. So let me quickly jump to another result here. So this is the map of the gas density, of the magnetic field strength, yeah, and of the metallicity at redshift 4. And you see that the magnetic energy here is very high. So we have almost 10 microgauss everywhere in the halo. And in the disk, we are 100 microgauss. So we have very strong field thanks to this subgrid dynamo. And then I'm going to give you an overview of the final result at redshift 0. So this is the disk we have at the end, a Milky Way-like disk, where you see this very nice thin disk. And that's the magnetic energy we get, the magnetic field, sorry, we get at the end, with magnetic fields around 10 microgauss everywhere in the disk, up to 100 microgauss deep in the center. And that's the halo magnetic field that you see with around 10 nanogauss everywhere in the halo. And of course, the disk being much stronger field. So I think I'm going to conclude by showing you a Faraday rotation map. So this is how you can compare to observations. And you see that we get Faraday rotation maps which are very consistent with observations. So the conclusion is that thanks to this subgrid dynamo, we managed to form very efficiently magnetic fields which are in complete agreement with observations. The trick is to use this subgrid dynamo to amplify the field only in turbulent high density regions. Starting from an initial field which is like the correct one, which is the one that the Biermann battery predicts, which is at 10 to the minus 20 Gauss. So without this subgrid turbulent dynamo, there is no way you can get such a high and fast amplification of the field. And you have to either go to crazy high resolution or you have to use other tricks. So I'm going to stop here.
Any questions for Romain?
I have a question, if I may ask. Really cool stuff, Roman. I reckon this is probably the only thing we're missing in terms of magnetic fields with Ramses. So I was wondering if you've compared at all your growth rates with, for example, the experiments that Christoph Federer was doing with turbulent boxes.
So yes, so the typical growth rate to obtain with this model is governed by it's basically the velocity dispersion at the scale of the cell, of the subgrid velocity dispersion, the subgrid turbulence velocity dispersion, divided by the cell size.
And this is exactly the growth rate you expect from turbulent boxes like Federat is doing. Okay. So basically, we reproduce the growth rate of the turbulent dynamo. Right? What's more debatable is how we handle the saturation. Yeah. This quenching parameter is really a free parameter, and it's probably resolution dependent. So some people claim that the quenching parameter should be equal to the magnetic Reynolds number, which in our case depend on resolution. And so it's 1 over the magnetic Reynolds number. And so if your magnetic Reynolds number that you get from your simulation is becoming larger and larger, 1,000, 10,000, the more you can afford, the better. Then of course this quenching parameter will go to 0, which means that the subgrid turbulent dynamo will disappear, right? Will gently disappear because at some point there will be no more significant amplification coming from this dynamo, because the saturation parameter will become so low that you might as well ignore it. And so that's one of the caveats of the present approach, is that you have to choose the quenching parameter by hand. I mean, and if you choose it too small, then your simulation won't be able to do the job because you won't be able to amplify the field high enough. If you choose it too high, then you will squeeze the magnetic field to a very narrow band close to equipartition. And then it's kind of a waste because you don't let the code do its job.
The other thing I wanted to ask you is, so when you have this amplification, you showed this R parameter, but you didn't tell us what is the magnetic field strength that you get after the dynamo, because you mentioned that you get further amplifications. I was wondering, is that below macro Gauss from what you're saying?
So what we get, if we choose Q equal 10 to minus 3, so if we choose the value we have adopted finally, then at the end of the simulation, we reach equipartition with the subgrid turbulence. And actually, if we have some result turbulence, which we do have especially at high redshift, then we get equipartition with the result turbulence. So we are in equipartition with the turbulence, whether it's resolved or unresolved. And so that's if you choose Q too small, then we drop below that. And if we choose Q too high, then you're going to squeeze, and you're going to get something which is like a narrow band around equipartition. Right? So we get equipartition.
Thank you.
Johan?
Yeah, just to follow up on this, since it saturates with the turbulence, you should see that the magnetic field is stronger at high redshift than low redshift. Because
exactly, that's exactly what we see. Exactly. Yeah, that's exactly what we see. I mean, I forgot to say it, but the phase space diagram I showed, right? The dashed line, the upper dashed line, was normalized to equipartition. And actually, the high redshift upper dash line was 1 order of magnitude higher, than the low redshift upper dash line.
Okay, so just to continue on this, so is it observed first of all, and second of all, does it turn into something in terms of the regular versus the small scale versus large scale magnetic field in the galaxy?
So it is observed. Actually, it's one of the hard aspects of explaining the magnetic fields in galaxies, is that they're actually stronger in the past than they are today. So you really need to have a fast dynamo to do that. So it is observed, yes. Now it's true that one of the key diagnostic that observations can help, ascertaining of this scenario is that turbulent galaxies at high redshift will have also a very turbulent magnetic field, while more quiescent galaxy at low redshift will have a much more organized magnetic field, right? And so looking at the magnetic field topology at high redshift versus low redshift could help us checking that this scenario is the right one, right? That it's actually driven by small scale turbulence and then rotation takes over. But if you're turbulent dominated, then of course your magnetic field should also be turbulent dominated, while at low redshift, if you're rotation dominated, then your magnetic field should be more toroidal. And that's what future observation could tell.
Any other questions for Romain? If not, let me thank again all the speakers of this afternoon, and we see you tomorrow at 9:30 for another galaxy formation session.